All right, thank you guys. Let's get started. A little bit of self-introduction. My name is Kevin Zhang. I went to MIT for my bachelor and master's, and then I went to Stanford for my PhD. Now I work in the AMD SerDes technology group. I mainly focus on high-speed transceiver circuits, which is also known as wireline circuits. And my main circuit blocks I'm an expert at is data converters, and I also look at some of the signal processing and algorithm stuff. On the side, in the past life, I do some technical writing as well. So if you Google circuit artists, you might find a blog that I've written some articles for. And then I also trying to bridge the CS and the EE world and hopefully convert some of the CS guys to the other side. And I do it through some open source SerDes modeling projects. So if you're interested, we can talk about it afterwards. This is the outline of my talk. So today I will start with an introduction of what wireline is all about. I will take you through a journey of some of the most critical wireline circuits and signal processing techniques from the transmitter to receiver, give you a little bit of a peek into what we're doing right now before I close with a summary. So why wireline, right? So whom after me might try to convince you that everything is wireless already, but but on the contrary, everywhere you look, there's a piece of copper connecting something, from the data center to copper trace on your PCB board. If you zoom onto your silicon, there's going to be a piece of copper wire carrying some sort of electron, right? So every one of them is a wireline, and as long as we're sending bits over them, we can treat them as a wireline link. With that said, right, this is how the trend has been going. This is a trend picture from last year's ISSCC. We're going to get a new one this year for sure. But in general, we have our own Moore's law, which is we're going to double the speed on the copper wire about every 4 years for pretty much all protocols, right? The familiar ones to you might be USB, HDMI. The ones that's kind of running under the hood might be Ethernet or some other stuff, right? So why is it a hard problem? Let's zoom in into what this piece of copper wire really is, right? So this is a typical cable that you will see in the data center. And if I send some sort of a sine wave into the copper, if I measure the sine wave coming out of the other end, you will see that the sine wave amplitude will get smaller, right? And I can now sweep the frequency of the sine wave and measure how much of that attenuation is, and basically plot this blue curve right here. And we call this curve the insertion loss of the channel. And the fastest speed you can send for a given data rate is given by basically the width of that bit, right, in time. And then that's going to give us what we call a baud rate or a symbol rate. And then when you look at the sine wave that completes the cycle, we're going to call this the Nyquist rate, right, which is half of the baud rate. If I go to this plot and find out what the Nyquist frequency is, and then read the y-axis off of it, that's my Nyquist loss. Right? We call this the Nyquist loss. So for this particular cable, I'm looking at about 20 dB loss for a 28 gigabits per second rate. Okay? And as you can see, if I keep increasing the speed, the loss is going to become higher and higher. So that's problem number one. The other side of a problem is related to energy. Right? There's a metric in wireline link related to energy efficiency. So it's milliwatt per gigabits per second. If you translate that into energy, that's picojoules per bit. That basically tells you, on average, in order to transmit 1 bit across that cable, how much energy you have to burn. And this plot on the right over here just shows you that there's an upward trend. The harder the channel, the more energy you have to burn to transmit that bit more reliably. And unfortunately, nowadays, there's usually a power wall. In the data center, you cannot burn infinite power. And conventionally, it has been 10 picojoules per bit. That's the magical number. And nowadays, that power wall has been going down significantly. And as you can see, the most recent ones, the red dots, are actually under 5 picojoules per bit. And then big companies are going to keep asking us to keep pushing that number lower and lower, right? So that's where the challenge is. Now, the demand then for this type of fast and energy efficient wireline link is still rising because of AI, because of all the other case, right? It has been internet before, then it might be crypto, then nowadays it's AI, right? So in order to build such a solution, we need to understand how a wireline links works. In essence, it's not that much different from the game of telephone, right? There's a transmitter on one side, you speak something onto the line, and then that line is going to add distortion and noise to your message, and then the receiver will try to recover that message to its best ability. So what's really happening in the circuit domain is you start with some digital information. These are the bits that you want to transmit. The transmitter's job then is to convert those information into a voltage in the analog domain. A higher voltage, low voltage, a positive one, or a negative one, right? That's basically what the transmitter is trying to do. If I overlay all those symbols on top of each other in a time domain, I can create something called an eye diagram. And then an open eye diagram might look something like this. It's not hard for us to distinguish what a 1 is and what a 0 is, right, from this eye diagram. What happens if I go to the channel? The channel, in essence, is a low-pass filter. So it's going to slow your signal down. And once it gets out of the other end of the channel, like I said before, it's going to be distorted, and then you're going to have noise on top of it. If I look the whole eye diagram exercise again, this is kind of what you're going to get. There's no easy way to distinguish what a 0 is or what a 1 is, right? Now, the receiver's job is trying to figure out what the transmitter said. And along the way, it might make a mistake, right? So when it makes a mistake, this is what we call a bit error, right? So let's look at a different domain. So we looked at the time domain. Now let's go into the probability domain. In the probability domain, the transmitter essentially only transmits 2 big sticks. It's either a 0 or a 1. What the channel does to the signal is that it kind of spreads out that information to a wider range. And there are some metrics that we can look at, right? One is the nominal strength of the signal. I call this H0 here. The other one is the spread of what the channel did to my actual signal, and that's the sigma. So we can come up with sort of a signal-to-noise ratio metric already. But what really matters is when I zoom in onto the tail. The tail is when one side crosses over to the other side. The area under it is the probability of that event, the crossover event happening. As a result, when it happens, we have a bit error, and then we call it a bit error rate. And it's a strong function of your SNR. There is technically no closed form in a real system, but they're often really strongly correlated. Okay? So ideally, what I want to do is I want to create something on the receiver side or even on the TX side to go back to a hard 0 or a 1. To the best of my abilities. So in order to do that, we have to zoom into the channel first, right? So here we're going to introduce a new concept called a single bit response. What I do is, instead of sending my data, random data already, I will send a single bit with some sort of a width. And that width is determined by my baud rate. And then the width of that in time, I call it unit interval. And then once I send that single pulse, and I look at what comes out of the other side, I will see something that looks like this, right? A harder channel is going to make that amplitude on the output smaller and more spread out in time, okay? And then instead of only having signal content at one UI, it can span across multiple UIs. And if I now want to send consecutive random bits, the output of the channel becomes a superposition of that single bit response because it's a linear system, right? Let's run through an example, right? So like I said before, I send one pulse. This is the pulse that comes out. Now I send a negative pulse because I want to send a 0. This is the negative single bit response coming out of it. I can keep going, right? Now, in the actual voltage domain, what you will see is when you have all these different color pulses added together on top of each other. But that's what's happening. But this picture is what's happening under the hood, right? If I focus on the red one right now, if let's say I want to figure out what the red is trying to send, I will actually have something called inter-symbol interference from my past bits and my future bits, because some sticks from other pulses is added on top of me. And this is an important concept in wireline communication called intersymbol interference. And our main job is trying to get rid of them, right? So here are some definitions. Let's start assuming that our biggest energy stick is called the main cursor. Anything before me is called the precursors. Those are the bits that happen in the future. Anything after me are the things that happened in the past. Those are called the post-cursors. So I want to build some circuits or use some signal processing techniques to cancel these ISI sticks, to bring them down to 0. And it's important to note that there's not a big need to actually reshape the pulse back to a perfect square wave, right? As long as all the other sticks are kind of zeroed out, you can still reliably make a decision on whether the signal is a high or a low. So what are the circuit components that we can use to equalize the channel, right? And by equalize, we typically mean we're compensating for the channel loss. So for the precursor side, typically it's the transmitter's job for reasons I will explain in the later slides, right? We use something called a feed-forward equalizer, or FIR, okay? And then the post-cursors is normally handled by the receiver side. We use mainly 2 types of circuits. One is called a continuous time linear equalizer. The other one is called a decision feedback equalizer. Yeah, we will see the fundamental operating principle for them in the next sections. With that said, I do want to highlight this picture though. There's actually the other half of the wireline link that I won't be talking about today, but it's equally important, which is related to time. Remember how we actually looked at some sticks in the single bit response? Those sampling point, or how reliably I sample at those points, is determined by these red blocks related to clocking. But like I said before, due to interest of time, today we're just going to focus on the voltage domain and try to open the eye. But I do want to drive that clocking picture home, which hopefully you will encounter in the future as well. With that said, that's a higher level summary of what wireline links are about, and we're going to dive deep into some of the equalization principles and circuits for it now, starting with the transmitter. So this is the picture I'm going to use heavily today, and we're going to start with an open diagram on the transmitter side, right? So this is what we start with. After the channel, which is a low-pass filter in nature, we're going to have an eye that's closed a little bit, right? In this particular case, the loss isn't that high. You can still tell the difference between 1 and a 0, but there are cases which we'll see later that makes it even tougher. So in essence, I want to invert what the channel is doing to my signal. So the opposite of a low-pass filter is naturally a high-pass. So if I create some sort of a high-pass filter on the transmitter side, which in the time domain kind of looks like this for an eye diagram, after the channel, it will become more open and cleaner. And then we say the channel is equalized, okay? So in the frequency domain, what happens is now the equivalent overall frequency response becomes flatter. What's happening in the time domain is I'm actually pre-distorting my transmit signal to be the opposite of what my channel is doing, so that once it comes out of the other side, right, the overall equivalent channel is having only 1 stick left. So what kind of circuit can achieve this? An FIR, in essence, in the mathematical domain is pretty straightforward. It just looks like this. It's a bunch of delay line where you're delaying the pulse and weighting them differently and adding them at the output. That's what an FIR is. And the reason why it's so effective and cheap on the TX side is because in the digital domain, you can implement an ideal delay. And that ideal delay is called a flip-flop. All you have to do is clock it with the right clock. You will create the right delay for the FIR. However, it's not all good with TX-FIR. There is something called peak power constraint on the transmitter side. What it is due to circuit limitations, your circuit cannot have arbitrarily large voltage on the output. So you're kind of limited by a maximum swing requirement. So in order to create this high frequency shape in the frequency domain, the best you can do is actually lower your DC gain. Now, this is illustrated by this kind of eye diagram over here, right? What the FIR is doing, it's not increasing the amplitude on the edges. It's actually reducing the inner eye diagram, right? So that the maximum swing stays the same. The high frequency action happens around this part. So as you can see now, I cannot arbitrarily make the eye smaller, right? Because the smaller it is, it will be smaller coming out of the other side. So typically, TXFR alone isn't enough for very challenging channels. A good rule of thumb is we typically constrain the equalization strength to within 10 dB on the TX side. So here is an example implementation in real transistors for a TXFR. As I said, the ideal delays either can be a flip-flop or there's something called a serializer that converts the parallel data bus and put them at the right position to emulate that delay. Once that delay is generated, the coefficients are created by different current amount, right? That's your coefficient. And when you put the currents in parallel, you're naturally creating a summing node. That's what the summing is, right? So here's an example for how a FIR on the TX side looks. Now, with that said, I'm going to shift gear and move on to the receiver side now, right? So I'm going to start with this picture again. Fundamentally, the big idea is the same. Instead of putting the high-pass filter before the channel, I can now put something after the channel, right? And then it can do essentially the same job because it's a linear system, right? So the first question to ask is, why not implement the same thing as the TX on the RX side? Can I do something like a FIR on the RX side? The challenge here is once it's after the channel, it's not a hard 0 or 1. We're not operating in the digital domain anymore. It's an analog signal coming out of the channel. As a result, in order to implement this, we need some sort of an analog delay. And it's essentially impossible to build e to the minus st in the analog domain, okay? So that's why for early links, we don't do this. Nowadays, there's a different scheme that we can do, which we can talk about towards the end. But fundamentally, we just need to now build a high-pass filter in the S domain, not in the Z domain. So this is how a realistic high-pass in the S domain would look like. You will have some sort of a 0 that gives you a rise in the gain, a pole that flattens it out, and another parasitic pole that rolls off because nothing is infinite speed, right? So another way to view this is I just need to create some sort of a tunable gain for low frequency with lower gain and high frequency at higher gain. What kind of circuits can give us that, right? So the first thing that comes to mind with a tunable gain is a source degenerated amplifier. You have a diff pair, all you have to do is have a resistor at the source, and now you have a knob to tune that gain, right? So this is what I want at low frequency. At high frequency, what I want is then I need higher gain. So the thing to do is to short it. Now I get the full gain of the amplifier, right? So which element behaves as a short at high frequency? It's a capacitor. All you have to do now is just put a capacitor across that resistor. You've implemented your first CTLE, okay? And then it's got this whole transfer function now because there's a impedance, not resistance, in the circuit. So I won't go through the pain of deriving this. So with the magic of, circuit analysis I've done some other time, this is the transfer function of a CTLE in this example. Right? It looks complicated, but I do want to point out it's mainly just 3 sections. One is the low frequency gain, as we talked about. The other term is contributing to how much peaking you're going to get in the CTLE. And eventually, there will be a term that's related to the roll-off. Okay? So if you ever design a CTLE, those are the 3 sections that you have to think about now. Right? As you can see, if I push the parasitics to higher frequency, you might get more peaking, but it could still be limited. The maximum amount is still limited by the middle term. So it's always a game of playing the trade-off between these 3 terms. So after now I have a high-pass filter both on the TX and the RX, I need a decision device, right? So now what kind of circuit can serve as a decision device to translate voltage into a digital bit. We're now in the domain of Dan's favorite circuit, which is a sense amp, right? So another way to view this is we actually need a device to have quote unquote infinite gain, because you need to, like, even the smallest voltage, you want to make it a hard 0 or a hard 1, right? And this is where the positive feedback comes into the picture, right? In circuits, we like negative feedback most of the time. As humans, we like positive feedback, of course, right? And this is one of the few cases where, you know, positive feedback is great in a real circuit implementation. So if I divide this circuit right here, which is known as a strong arm latch, it's nothing but these two sections. There's a section that looks at input, creates an initial bias for your positive latch, and then the positive feedback circuit, as you've seen before as a sense amp, will now bring the decision one way or the other. Okay? So here's what we have so far. We have some high-pass filter on the left side, some high-pass filter on the right side. We know how to build the circuits, and then we know the decision device that we just built, right? What's missing is I haven't talked about noise yet, right? So noise is this random process, and in the frequency domain, this floor that's going to be added on top of your circuit. So how do the circuits perform with noise? If I look on the TX side, I know I have this peak power constraint. So if I want to equalize the channel, I will lower the DC gain. But the more I lower it, the final output on the other side of the circuit is going to get close to the noise floor. Once you get too close to it, you're limited by the noise. You cannot tell a difference between noise and the actual signal, right? What about on the RX side? Again, it's a linear circuit, so it knows nothing about noise and signal. It treats them in the same way. So it will amplify the signal, but at the same time, it will amplify the noise. And there's a limitation there. Is there any way we can get around it? And this is where decision feedback equalizers come into the picture. A decision feedback equalizer has that decision device, the comparator, in the feedback loop. It looks weird, right? Let's walk through an example of how it actually does it, right? So if you have a single bit response come in, and assuming I know what the previous bit is, I now can have that feedback loop and subtract that signal energy from it, precisely. And then what's left over is this funky looking shape. But from our beginning, like the start of the talk, as long as the ISI at that point is 0, I still can reliably tell what the signal is, right? So now in order to get around with the noise problem, we introduced this nonlinear equalizer. A DFE is a nonlinear equalizer simply because there's a nonlinear device, that comparator, in the feedback loop. And because the decision is quote-unquote noiseless, it already taken out the noise. There are only two options, and that's how we can use it to do very precise and controlled ISI cancellation. And unfortunately, one limitation for the DFE is that because it's only looking at your pass bit, you can only cancel post-cursor with the DFE due to causality. I wish a DFE can know about my future, but that defeats the whole purpose, right? So now you can go crazy with this, right? If I know that I can precisely cancel an ISI, I can obviously keep delaying my data and figure out what the right signal strength is at each of these sampling points and kill them completely, right? So as you can see, here's an example. The red is a pre-DFE single bit response. The blue is a post-DFE single bit response, and then their corresponding eye diagram looks completely different. One is very clean, the other one is fuzzy, right? So there's another field or another related topic, which is about how to find those DFE feedback values, which is related to adaptation. For the interest of time, I won't talk about it, but hopefully later on you will see what I mean during the break time. Now, again, it's not the superhero that we all think it is. There are obviously limitations and trade-off for any circuits we do. For a DFE, there are mainly three things. If you go completely crazy on the number of taps you have, you're going to overload that summing node. There's going to be a lot of circuit that's on that node, and then you're slowing yourself down again. So the return of investment by adding one more tap will go down. Okay? So there's a limit to that. The second one is, so far for DFE, we've always assumed the decision is right. What if I made a wrong decision, right? Just like, our real life. If I made a wrong decision in the past to inform myself now, maybe I will keep making the same wrong decisions over and over again. And there's a field called DFE error propagation that people use statistical modeling and Markov chains to study. And I just want you to be aware of that. And lastly, perhaps the most well-known for decision feedback equalizer limitation is any feedback loop has this stability constraint. And for a DFE, the stability constraint can be formulated as the following. The feedback loop itself, the timing closure has to finish within one UI. So each circuit element in this feedback loop has its own effective delay. So I have to make sure my feedback makes in time before the next signal comes in. And that's what the feedback limitation for a DFE is. There are implementations to get around with this problem, but we can talk about it during Q&A as well. And just for completeness, here's an example DFE implementation, very similar to the TXFIR that we said, except now the flip-flops and the summing is in the feedback path. Note that here you can actually combine the concepts we talked about. The CTLE can be part of the DFE equalizer as well with the simple source degeneration. So now you have a feed-forward path, that's a CTLE, and a feedback path, that's a DFE. So putting it together, this is what we talked about. On the left-hand side, this is the output of a high-loss channel. The eye is completely closed. You can't tell 0 from a 1. You add a little bit of a TXFIR, you're opening the eye a little bit, but it's still hard. In the presence of noise, you can still make a mistake. Then you add the CTLE, it gives it some signal boost, but you can open up the eye a little bit more. Eventually, the DFE does all the dirty work and clean this thing up and really open up the eye. So with that, I'm going to give you a sneak peek of what we are working on nowadays and where the field is kind of going. Right? Let's bring back this picture one more time. So something happened around this time frame between 2010 to 2016. That's when I got my PhD, about that time. Right? And then that speed is about 28 to 56. Okay? And if I look at this representative channel on the right, at 28 gigabits per second, this is the Nyquist frequency we talked about. It's about 20 dB loss. It's a reasonable loss. People can still reliably recover the signal at the output of the channel. Now, if I want to extrapolate now, if I want to double the data rate, I have to now go to 28 gigahertz. But this channel will become very challenging to do so because, as you can see, at 28 gigahertz, this particular channel has a big suck out. It has a notch in the frequency domain. Basically means anything you transmit at that frequency is gone. There's nothing you can get through that channel. And even if the channel doesn't look like it, if I extrapolate it linearly, the nominal loss for that particular channel is about minus 50 dB. Right? That's more than 100 times attenuation. So at the time, keep scaling the frequency for this kind of channel didn't seem viable at all. Right? So what can we do? Well, at 28 gigabits per second, we can, again, do the hard work of trying to double the frequency and work extra hard on our equalizers, right? Another way is now people looking to doubling the information. So every time, instead of transmitting 1 bit, how about we transmit 2 bits? I think Vivek on the optical side will talk more about this as well, right? So then you have 4 levels, and that's what we call PAM4. Right? That's what that 4 means. Every time you make a decision, you extract 2 bit, and that's how you double the effective data rate. The challenge here is, of course, the hardware complexity is going to go through the roof, and it's still an active design and research field to get that performance and implementation cost down. And last but not least, this is the complete picture today. So everything kind of moved into a digital to analog, back to digital kind of signal processing chain. And this is in order to support that PAM4 modulation I just showed you. However, the same equalization principles we discussed today still apply. It's just I'm not implementing it in the analog domain anymore. I'm just doing math in the digital domain. The key here then is to design a reliably good digital to analog converter or analog to digital converter. And that brings me to my summary. So hopefully today has been an eye-opening experience for you, pun intended, right? And then we talked about TXFIR, CTLE, and mainly DFE, right? And during the break time, I will bring up a demo on my laptop where I will show you, how I use CS to help you visualize more, how the eye diagram equalization works. Okay? So feel free to stop me. Right? But let me bring back the full circle and ask why wireline again. Right? So I hope I've convinced you that it's a very interesting field and it's still very relevant today, maybe on different scales and for different applications. Even though it seems like we're very close to the physical limit of copper, it's still probably the most cost-effective material that we humans can send bits over, right? So there's always a push to continue that application. And as you've seen, the whole wireline field has converted into a digital to analog to digital kind of chain. And this is a common theme across all fields. And then I hope you will see that theme in wireless and optical as well, right? And last but not least, learning to design a wireline circuit, as you've seen, requires a lot of a holistic view and understanding on both the signal processing, the system algorithm, as well as circuit design. Right? And I want to close with this picture right here. So really, what I've done today is just scratch the surface of the iceberg. There's a lot more going on under the hood, and I'm open to answer any questions related to this picture right here. So with that, my talk is finished. I will welcome you for any questions.